Okay, sure.
And it's okay. It's okay.
All right, welcome everybody. So Chris has the distinct pleasure of having not just one, but two PhD advisors. Jeanette, the primary advisors, and myself. So maybe Jeanette, you can go first.
Sure, I'm going first. So this is Chris. Chris has been in part of mine and Marco's lab for a few years right now, and he will show you all this amazing work that he has done while being part of our lab. I'm really looking forward to it, and I hope you enjoy it as well, as much as we enjoyed working with Chris during all these years. Yeah, and Chris has done a lot of other contributions to our labs, including running running a bunch of social events,
Advising students.
Of course,
Yeah.
a lot of them, doing the grunt work of teaching as
Yes.
well, and robot autonomy, which I'm sure many of you have experience with, how much work that actually is. And yeah, I can't wait for seeing what's coming next if you pass, which you still have to decide, of course, but yeah.
Thank you.
Well, sure, a couple of words for myself as well. So I think Chris is the embodiment of the new generation of roboticists, really thinking about several new topics, for example, related to data curation, data attribution, that are currently key topics for the development of autonomous stacks as we know them. Chris also made several contributions to our lab beyond just technical contributions. For example, serving in the ASL team for the Duran Cup and allowing us to win at least once. So we're very grateful for that, and also advising a lot of students on our side as well. And last but not the least, he has been able to put up with two advisors. So it also showcases its diplomacy skills.
Hardly a challenge. Hardly a challenge. Well, thank you so much for the introduction, Marco and Jeanette. And thank you all for being here today. My talk will focus on how we can make robot systems, particularly those driven by learned policies, more reliable, as is needed for their deployment in the real world. So the past decade marks a period of tremendous progress in robotics, where systems once confined to very repetitive automation tasks in very controlled settings are gradually shifting towards more flexible operation in semi-controlled environments to where we are today, where there are raised prospects of systems that can intelligently operate within the unstructured context that characterize our daily lives. Now, much of this progress has been enabled by a shift toward a data-driven paradigm for robot learning, where rather than manually programming robots for each new task in each new environment, we instead train behavior models that can control robot systems to execute many tasks, and we train them directly from data, thereby allowing a single system to scale across many tasks and environments. Progress within this paradigm has been accelerated through several reinforcing developments, namely larger data sets, more sophisticated learning algorithms, coupling internet-scale knowledge with large generative policy architectures, which are coming together to result in policies that have broadened capabilities suited to human environments. For instance, policies that can cook you food and plate them for you, or even policies that can control humanoids to perform very human-like locomotion behaviors, almost scary behaviors. And while these policies are becoming more general in their capabilities, they still make mistakes. They're not perfectly reliable. For instance, you wouldn't want a robot doing this in your house. And often these mistakes can be extremely costly, potentially even risking the safety of people around them. So this leads us to the question, what challenges currently prevent us from building reliable solutions using learned policies? And there are several spanning both the development and deployment life cycles of this technology. The first is that of data collection. By definition, the performance of a data-driven system is determined by the quality of its training data. However, building high-quality training data sets, those that support reliable deployment of these models, is still an open research problem in the field. The second is interpretability. We currently lack principled techniques to determine the root cause of undesirable behavior from these black box models. And these first two problems live at the level of policies themselves. The third problem goes beyond individually learned behaviors and is related to the high level intelligence needed to take an environment from the state on the left to the one on the right, which entails coordinating behaviors for multi-step tasks. This problem lives at the level of systems built atop these learned policies. As a result of these challenges, policies today remain unreliable. Without high-quality training data, they may fail unpredictably or even exhibit hazardous actions in their environment. And when they do without interpretability, their root causes remains opaque to us designers, which blocks systematic improvement. Without high-level intelligence, systems built atop these policies will remain restricted in scope to tasks that are short and well-defined, while multi-step novel tasks, the ones that are really tedious for us, remain unreliable. So we will be discussing mechanisms to improve deployment time reliability, specifically those that strengthen behavior of these systems at deployment, safeguard them, and interpret deployment data with respect to the data that these systems have been trained on for subsequent end-to-end improvement. With our overall objective being to enable robots to remain performant and trustworthy under varying deployment conditions and complex task settings. In other words, to be reliable. To this end, the first part of the talk will focus on policy monitoring and interpretability, and the second part of the talk will focus on policy coordination and planning. All right. So some of the most capable policies today are those that have been adapted from foundation models pre-trained on the internet, thereby bringing internet scale knowledge into the robotics domain. This has allowed for policies to solve tasks that they've never seen before, such as moving a fruit to a flag, or even asking a model to move a Coke can toward Taylor Swift. Now, this is proving to be a scalable recipe to train policies that can perform many different tasks, sometimes even those they've not been explicitly trained to do. They still show diverse failure modes on tasks they have been trained on, often resulting from very subtle, imperceptible shifts that occur in their environment, making them extremely difficult to catch. And even if these failures are rare, the ability to detect them at deployment is really a necessary condition for scalable and trustworthy robots in the real world. So our research question is, how can we reliably detect novel failures at deployment? The key word here being novel failures, because policies that operate in, that are deployed in open-ended environments are never guaranteed to fail the same way. While it's great that we have failure detectors that can catch failures we've previously seen, we need them to also detect failures we have never seen before. Existing approaches monitor for out-of-distribution inputs. So given some samples from the policy's training or nominal deployment distribution, which may look like this, these methods will classify failure based on some measure of difference or dissimilarity of a new test scenario with respect to the nominal distribution, which is great if the policy fails. However, as we have already seen, there are cases in which a policy, particularly those that have been internet pre-trained, fail despite an environment shift appearing larger, causing these kinds of failure detectors to raise many false alarms. In other words, the key takeaway is that for policies, visual difference or dissimilarity does not necessarily imply failure. Now, this constitutes a common failure mode for two popular classes of OD detectors, namely embedding-based and reconstruction-based approaches. While there are uncertainty quantification techniques, which often involve training many versions of a model, running them in parallel, or actively computing model gradients, these approaches don't really scale well to the kinds of large generative policy architectures we use these days that produce actions over hundreds of forward passes, such as diffusion policies. So the question remains, how can we detect failures without failure data? For some preliminaries, we assume we are given a generative policy, one that predicts a sequence of actions h time steps into the future that is trained on a finite horizon task, for instance, to close a box with 3 lids. And we're going to execute this policy in a receding horizon fashion where we sample h actions from the policy, execute the first k of those h actions, and then repeat at time step t plus k. In other words, for a policy that predicts 4 actions and executes 1, the rollout kind of looks like this over time. Now, our observation is that subtle distribution shifts result in highly diverse failure modes, the policy stalling amidst its task, the policy pulling away from its object of interest, colliding with the object of interest, or in some cases getting stuck and exhibiting this really unsafe, jittery failure. Now, however different these failures may appear to us, the key insight here is that they all represent an instance where the policy is no longer making progress on the task. Therefore, our first proposed solution is to use vision language models to monitor the task progress of a policy during execution. And we do this in a video question answering setup where we pass the history of policy observations to the VLM, along with a prompt containing the task specification to a VLM, after which it performs some generative reasoning and outputs a failure classification. And we do this because state-of-the-art VLMs have been shown to possess task-relevant knowledge that we can elicit for the task of runtime monitoring. So applying this strategy across a suite of simulated and real-world cases actually performs quite well. This monitor is able to catch 85% of failures, raising only 7% false alarms. The challenge is that autoregressive generation with VLMs is actually quite slow. Depending on the prompt, can take up to 10 seconds for these models to return a classification, which may be fine for the kind of failures that occur over very long timescales, but not so much the ones that occur over shorter timescales, which are also those that tend to be safety critical. And so our core idea here is to partition failures into categories and assign them to specialized detectors suiting the requirements of that category. The first is that of slow task progress failures, which, as we've shown, we'll assign to VLMs. And the second is that of fast, potentially erratic failures from the policy, which we will detect with a temporal output consistency. So our proposed solution number 2 is to measure how much a policy's action distributions are changing over time as a proxy for whether the policy is failing at deployment. And we do this by computing temporal consistency scores over overlapping actions of a policy during execution. Specifically, we compute statistical distances between overlapping segments of the policy's action distribution throughout a rollout. And we show empirically that the policy's inconsistency tends to grow faster when it's failing than it does when it succeeds, which allows us to calibrate a detection threshold to an upper quantile, the 1 minus delta quantile, of successful policy rollouts. In other words, we can construct this detector using only successful examples of the policy's execution and then use it to catch failures we've never seen before. And in this illustration, you can see how when the policy fails, those action distributions between the current and previous time steps, shown here in blue and yellow, tend to diverge. In contrast to how these distributions heavily overlap when the policy is succeeding. Our overall method combines both detectors in parallel, both the temporal consistency detector and the VLM, and raises an alarm if either of these detectors issues a failure warning. Empirically, the first result we find is that naturally, by combining detectors, we expand coverage over unknown failure modes. The combined detector catches more failures than any one of the individual detectors. In the worst case, when we combine detectors in this way, we compound their false positive rates, but the overall system remains reasonably practical, only an additional 6% in false alarms, if and only if both individual detectors comprising it have a high true negative rate. And lastly, we are able to improve safety by significantly reducing detection time. The combined detector is able to catch failures 40% faster than using the VLM alone. To recap so far, we've proposed 2 methods for detecting novel policy failures without assuming any access to failure data. And we've demonstrated that combining these detectors yields complementary coverage of failure modes. All right. Now, runtime monitoring can help us detect failures, but they don't help us get at their root cause. The observation here is that the failures of a learned policy can almost always be explained in terms of their training data. So let's assume this is the support of a policy's training experience, the set of scenarios in which we would expect the policy to perform competently, and we'll consider 2 failure cases. In the first failure case, the test scenario relies beyond the data support, in which case our solution is relatively straightforward. It is to collect data around that test scenario to expand the operational competency of our model. In the second failure case, the failure lies within the data support. Now, this is a particularly difficult failure case to address because it requires understanding how the training data shaped the policy's behavior when it failed, which is difficult because we often view policies as black boxes, an uninterpretable set of weights trained through hundreds of thousands of iterations of a stochastic gradient descent algorithm on a data set whose properties we often don't fully know. So concretely, we assume access to a data set of demonstrations, which may teach a policy to perform a task like tying a knot. And we train our policy using behavior cloning, standard maximum likelihood objective, and evaluate the policy on the robot system based on its expected return. Typically, this is the success rate of the policy. The thing to index on here is that the closed loop performance of the policy on the robot system is intimately connected to the quality and composition of its training data. Now, if the policy exhibits undesirable behavior on the robot system, we currently lack principled strategies to debug policies as a function of their training data to improve their end-to-end performance. In other words, we know how to go forwards in the process, not so much how to look backwards. So if we want to connect these concepts, we need a way to relate how demonstrations shape deployment time performance. And our proposed idea here is to establish this relationship by answering counterfactual questions about how training data affects the policy's expected return. Questions like, what would happen to my policy's performance if I added a new demonstration or removed an existing one from the training data set, which entails estimating a performance counterfactual, the difference in the performance of a policy trained on all the data and a policy trained on all the data minus a subset, minus a trajectory of interest tau. Now, of course, empirically estimating this performance counterfactual is totally not scalable because we cannot train policies on all subsets of our data and evaluate them all in the robot. So our insight here is that we need to do so predictively. And we do this by making a first order Taylor approximation to this performance counterfactual, where we start by training a behavior cloning policy by minimizing the total loss across all demonstrations in our data set. For the sake of analysis, we'll then consider this perturbed objective, which is our original BC objective, plus an epsilon weight on a trajectory, demonstration trajectory of interest. Then we introduce this concept called the performance influence, which essentially captures how small changes in the importance weight of a training sample of interest affects linearly changes in your policy's performance. That influence function breaks down into two terms. The first is the policy gradient, which is a term we commonly see in reinforcement learning. And the second is a term that is perhaps less familiar to roboticists, which is called the parameter influence function. Now, this is a quantity that's well studied in the broader machine learning literature, and there are plenty of tools for estimating this quantity. Okay, so by virtue of the performance influence having the expected return, it is reasoning over the outcome of sequential closed-loop decisions from the policy. The problem is we cannot directly compute it because we don't assume access to the dynamics of the system, nor do we have access to the reward model. And this differs from the typical use of influence functions, where they tend to be interested in figuring out how changes in the importance of training samples affects test or validation losses. But this is less relevant to what we do in robotics because it's well known that validation losses are often not predictive of the closed loop performance of your system. Moreover, when we execute policies in the real world and they fail, we often don't have ground truth actions for those rollouts. Instead, what we have are reward signals. So our proposed solution here is to leverage the log derivative trick underlying policy gradient methods to decompose this performance influence into a tractable sum of quantities, which is our final estimator for the performance counterfactual. Now, in the interest of time, I won't go through all the details of this equation. I'll tell you what it entails. First, we train our behavior cloning policy to convergence. We then evaluate it on the robot system, yielding a set of rollouts along with their associated return, +1 if the policy succeeded, -1 if it failed, which we use to approximate the outer expectation. And then we iterate over states and actions of our rollouts and the demonstration of interest, and use existing influence function machinery to compute this inner term. In essence, this equation is allowing us to causally relate the effect of one training demonstration on the policy's deployment time performance. Now, the question is, how can we systematically improve performance? We propose to do so using the performance influence as a means to curate training data that most strongly impacts the policy's downstream success rate. We do so by taking any training demonstration or a demonstration from a newly collected data set and using this performance influence to score these demonstrations and rank them based on their contribution to downstream success. We then select the top K demonstrations, resulting in a curated data set that we use to retrain our policy. This is the Cupid data curation algorithm. Now, we, in experiments, evaluate many different scenarios in which properties of the data set may adversarially affect the performance of your policy. First, we look at a mixed quality curation setting where the data set contains some trajectories that are high quality. They very smoothly and consistently execute the task, and other demonstrations that may contain some retry behaviors or some suboptimal behaviors. We also consider a tuck box scenario. This is a data set that contains multiple strategies. However, some of those strategies are rendered unreliable by distribution shifts at deployment time. For instance, if we alter the mass distribution of the recycling bin, the sliding strategy, where we slide the box underneath the rack, becomes unreliable, whereas the pick and place strategy remains reliable. And lastly, in the most challenging case, we consider a data set that spuriously correlates demonstrated behaviors with the color of the background, which may cause a policy to execute the wrong behavior at test time based on the presence of the spurious correlate, which is the white background, as opposed to the task relevant feature, which is that at deployment time, there's a stacked book on top of the target book that we would like, requiring the robot to pull out the target book vertically so as to not let the book stack fall. Well, we find that applying our data curation algorithm in the mixed quality setting is able to filter out low quality demonstrations, resulting in a policy that has consistent task progress. Similarly, applying our data curation method to the tuck box case, we're able to prune brittle strategies by attributing sliding behavior to failure. And lastly, by attributing samples with the white background to a common cause of failure, we're able to apply data curation to rebalance the data set, in turn eliminating spurious correlations, resulting in a policy that exhibits this vertical retrieval motion. Across domains, we find that Cupid performs quite well, and we compare it to a few different baselines in data curation, some of which perform very well in some domains, but not all. And the key takeaway from these results is that the performance influence is a standalone signal that can be used to address various root causes of failure, whereas some baselines may only be applicable to some causes. As an ablation result, we also apply our method to curate data sets for single task policies and use those data sets to fine-tune a multitask policy that can complete several tasks. And we find that this also improves the performance of a VLA like Pi0. So our third contribution here is that we've established a causal relationship between training demonstrations and policy performance. And then we've developed a data curation on top of this methodology that maximizes deployment time success. The overall outcome is we've now enabled policies to remain trustworthy and performant under varying deployment conditions by using runtime monitoring to safeguard their behaviors, data-centric interpretability tools to understand the root causes, and dataset curation to improve performance. And this takes us to part 2 of the talk, policy coordination and planning. Now, just because we can reliably execute individual behaviors doesn't mean that systems built atop these behaviors can reliably execute tasks. While many such tasks, like shelving kitchenware, packing a luggage, or loading a dishwasher, indeed require executing behaviors in sequence, critically, being successful at these tasks requires carefully coordinating how these behaviors are executed to resolve implicit dependencies in the task. Now, this coordination burden is sometimes felt by us. For instance, we very carefully strategize how we pack our carry-on, while we may not overly think about how we place the first cup at the back of the shelf before placing cups at the front of the shelf. Now, this is also a challenge faced by robot systems, except a little bit more acutely because robots operate under stricter kinematic and geometric constraints than we do as humans. For instance, the robot may pick up the cup in this case in a way that makes it kinematically infeasible to place it in the cabinet, whereas a solution that picked up the cup by the handle would afford this subsequent placement. So notice that there's nothing inherently incorrect about the way that the system had picked up the cup in the first case. However, that grasp becomes incorrect when considered within the context of the full task. There are existing methods based on task and motion planning that can generate these coordinated long horizon behaviors, typically through gradient-based or sampling-based optimization. Some common assumptions behind these approaches are that they assume full state observability. That is, they assume knowledge of the position and orientation of all objects in their environment, down to the fine-grained geometry of these objects, for instance, meshes. They often use simulators in the loop of planning to simulate forward the effect of actions into the future. And if they don't use simulators, often there is some hand-designed dynamics models to predict these effect on states. Now, the thing to observe here is that these assumptions stand in striking contrast to the advantages we get from our model-free, data-driven approach to robot learning. Specifically, that behavior policies do not require full-state observability of their environment, and they can often perform tasks that are very difficult for us to model. So our question becomes, how can we get coordinated behaviors from a system that is built upon learned policies? Some preliminaries: we assume that we are given a library of learned behavior policies that can pick up objects, place them, pull them, push them. And here we assume a library. This could also be one policy capable of performing multiple behaviors. And we make one simplifying assumption, which is that these policies will be executed in open loop. That is, actions sampled from the policy at the very first time step will be used to determine the behavior of the robot or what's executed on the robot in subsequent time steps, in contrast to what we previously saw, which is a policy that makes predictions throughout the rollout. The second thing we assume is a sequential manipulation task, a sequence of policies that we'd like to execute in the environment, where the task contains these implicit dependencies we need to resolve. In this case, picking up the hook too close to the bend in the handle does not give the robot enough reach to pull in an object of interest outside its workspace. Our proposed idea here is to formulate the behavior coordination problem as a maximization problem over the joint success probability of the entire policy sequence. So we assume we're given this sequential manipulation task, a sequence of H policies we want to execute from the initial state S1. And then we consider the joint success probability, which is simply the probability that all policies in the sequence succeed. That is, they achieve a reward of 1 in a binary reward setting, given actions or behaviors sampled from them, A1 through H. We show that this joint success probability can be expressed as a behavior coordination objective, which is the product of each policy's respective Q function evaluated under states predicted by dynamics models. And so our method here is to optimize the behaviors or actions of all of these policies in a sequence with respect to the product of Q functions behavior coordination objective. Now, you may ask, where do these Q functions and dynamics models come from? Our approach is generally agnostic to how you choose to learn them. However, we learn them using standard actor-critic methods in simulation. So we apply a sort of standard actor-critic methods like soft actor-critic, and we use the replay buffer from these simulated rollouts to train dynamics models. Our method is also agnostic to the way we perform optimization. So you can use gradient-based optimization techniques. We have experimented with many sampling-based optimization techniques, such as the cross-entropy method. Now, evaluated on the robot system, our behavior coordination objective is able to, in this case, inform a pick of the hook that affords sufficient reach for the robot to pull the object of interest in. In the second case, our coordination objective actually addresses a unique, peculiar pitfall of simply executing policies one after another, which is that the policies themselves may be imperfect. And by performing additional refinement on top of them, we're able to plan around these imperfections of the policy. And finally, in the most complex setting, figuring out where to place the object of interest so that it can be pushed underneath the rack, which is a particularly challenging case because there is so much room, the action space is so large in which the object could be placed. Across all these domains, we find that our objective is able to significantly improve performance on never-before-seen sequential tasks by 42% over myopically executing skills one after another. And perhaps more interestingly, we're able to show that the product of Q functions is able to very closely predict the joint success probability of the sequence. We show this by first establishing a pseudo proxy for the joint probability of task success using simulation and a brute force search. And in the first case, we apply our method with a random shooting optimization strategy where we randomly sample the action spaces. And this really doesn't perform too well because of the curse of dimensionality. The search space here is really big. Warm starting the optimization with actions sampled from the policy brings us a little bit closer to this ground truth task success probability. And then performing cross-entropy method, essentially iteratively refining our sampling distribution over time, brings us very close, with the added benefit that our algorithm runs 4 orders of magnitude faster than relying on simulation, on average around 100 milliseconds. All right, to recap, we formulated behavior coordination for learned policies as the problem of maximizing the product of Q functions. And we've also showed that the product of Q functions is predictive of the joint success probability for policy sequences. One final problem. We assumed a step-by-step plan. We assumed that we gave a policy a plan in the form of pick up the mug, place it in the cabinet, which, as you can imagine, doesn't really scale well to these kinds of environments. If you have to tell a robot system to pick up the green pot, place it in the dishwasher, and so on and so forth, you might as well do the task yourself. And so this really highlights a requirement that we need robots to be able to interpret instructions issued in natural language instruction, the same way that we communicate with each other. Put everything in the dishwasher. So, existing methods turn to language models as robot planners from natural language instructions. And the common strategy there is to repeatedly execute the next best action in the environment according to a combined LLM and affordance score. Here's a representative method called SayCan from Google, which, given the instruction, I spilt my drink, can you help? First generates a set of candidate next actions the robot system can take, scores them with the language model, and then combines these scores with the affordance, the feasibility of each of these actions in the environment, essentially situating a language model on top of the behavior policies, resulting in one closed loop system. However, as we've already seen, executing skills one after another myopically may result in unresolved dependencies. So the logical solution here would then be to use our behavior coordination method to resolve these behavior dependencies before we execute them in the environment. However, this surfaces yet another challenge about plans produced by LLMs. Specifically, while these plans may seem valid at a high level or at a symbolic level, there may be no feasible solution that exists in the real world due to geometric or kinematic constraints of the environment. So how can we find feasible plans of learned policies from language instructions? Our proposed solution here is to use our behavior coordination method as a means to guide the construction and search for feasible plans generated by language models. until we find a plan that's feasible in the real world, upon which we execute it. In this case, the robot must first place the cup back on the counter, pick it up in a way that affords a placement in the cabinet. Naturally, there are multiple ways in which we can integrate our geometric behavior coordination algorithm with a language model. The first of which is a shooting strategy, where we use a language model to generate k possible sequences or task plans, each of which we refine using our behavior coordination algorithm and execute the one that is feasible in the environment. Now, this is a very computationally efficient approach because it only requires querying the LLM once for plans. However, plans generated by the LLM in this way may not be feasible in the environment. So the second approach we investigate is to conduct a search using the LLM and our coordination planner. And the way that works is that at each iteration of the search, we ask the LLM for a candidate set of k possible next actions, each of which we coordinate within the context of all the skills that have come before. In this case, this is the first search iteration, and so there isn't a plan that exists before. And we incrementally build up a plan until we find one that is feasible. Now, in this case, by grounding the search in feasibility from the very first step, we're much more likely to find a plan that can be executed in the real world. The downside is that this approach is very computationally expensive because it requires querying the LLM numerous times during the search and also querying our behavior coordination algorithm numerous times. Now, this represents another setting in which we have multiple methods that have complementary strengths. And so our final approach attempts to integrate those strengths in a hybrid planning strategy. We call this text to motion, where we first attempt to perform the more computationally efficient shooting strategy. And if no feasible plans are found, we fall back to take a single step of search, after which we will attempt shooting again. And if a feasible plan is found, we will then terminate the search. This allows us to build a system that can now translate natural language instructions directly to plans that can be executed by robot systems in the real world. Including plans that, or including instructions that contain very abstract concepts such as primary colored objects, in this case, eliciting the semantic understanding, requiring the semantic understanding of language models, while coordinating dependencies at the physical level. Great. So our third contribution here is that we've introduced a language-based task and motion planning framework for learned policies by verifying the correctness of LLM-generated plans on the physical level. Collectively, these contributions build higher levels of intelligence into robot systems driven by learned policies, enabling them to remain performant in complex and multitask settings and multi-step task settings. So this brings us to our conclusion. To summarize, our overall objective was to enable policy-driven robots to remain performant and trustworthy across varying deployment conditions and complex task settings. In other words, to promote reliability at deployment. Our overall thesis was that the reliability of these systems could be advanced through a complementary set of mechanisms that operate around learned policies, reinforcing them at their points of fragility. Of course, alongside continued advances in the development of policies themselves. And therefore, our approach was to identify and address these deployment fragilities at both the policy level and the system level. To this end, we looked at both policy monitoring and interpretability mechanisms, as well as policy coordination and planning mechanisms. In terms of directions for future work, there are several. The first of which is scaling data-centric research, tapping into large, potentially noisy data sources for robot learning, such as human videos, which may motivate the need for curation algorithms. The second is model explainability, so going beyond the sort of numeric or quantitative insights we get from the influence function-based techniques we investigated in this talk, to surfacing human interpretable insights that allow us to improve these policies. And finally, to leverage emerging model classes like world models to address reliability-related challenges, such as safety evaluation, efficient robustness testing of policies, or even developing new policy architectures based on these models. Here's a full list of publications that I worked on throughout my PhD, and I'd like to thank you for your time. Before going to the Q&A, I'd like to do some acknowledgments. I'm going to start with my advisors. First, Jeanette. Jeanette, before you decided to advise my PhD, you were first assigned to me as a faculty buddy. And I still remember receiving a call from you telling me about my admission to the Stanford PhD program. I remember accidentally missing that call and then wondering what I should do. Overall, I'd like to thank you for taking a chance on my PhD, despite having relatively less exposure to topics in manipulation early on. I'm extremely grateful for your generous time and all the effort you put into helping me shape the foundations of my research skills and approach, and especially grateful for the very active role you took in creating opportunities that would require those skills to grow. I think all of your students would agree that your passion for robotics is totally contagious, and that you set an example for putting that passion into a very rigorous and creative research process. So thank you. Marco, your guidance has been invaluable in my PhD. Thank you for imparting to me the importance of always searching for deeper insights and nuance in everything I work on. This has played a pivotal role in the way I look at problems and the way I assign value to problems as a whole. Thank you as well for finding opportunities that would require my skills to grow beyond my immediate research, for instance, in mentoring students. And I know that we didn't get a chance to put an LLM in space, but there is still time. A few weeks left in the quarter. But it is this commitment to excellence and this sky's the limit mentality that I think gives us students the confidence to take on problems bigger than ourselves. To the broader defense community, Clark, thank you so much for agreeing to serve on my defense and my reading committee. As this presentation has tried to convey, I think safety is an absolute keystone for robotic systems, only growing in importance as robotics has the potential to enter into human environments. And there are also so many different ways in which we can go about safety, all of which need to be explored. I think your work is amazing, and I'm really glad to see students like Milan choose to work at the intersection of safety and robotics. Michael, thank you so much for serving on the Defense Committee. Thank you as well for hosting me at all the TRI meetings throughout my PhD. Your questions always demonstrate a very genuine level of engagement with the topics I was working on, and often provided me with some insights and perspective that I would take home and think about to inform next steps in research. I also think that there are many papers I read that are formulated as MDPs, which should very much be POMDPs. Finally, Eero, thank you so much for serving as defense chair. This is a very full circle moment and experience for me because, as mentioned, my undergraduate work, the reason that I'm at Stanford, it was actually predicated on the work you did in your PhD, specifically on 3D explicit scene representations and figuring out how to do task planning for robot systems in those representations. And I think the concepts I learned reading your papers very much sit beneath the surface of several of the papers I presented here today. So thank you. To all my collaborators, I think it goes without saying that none of this work could have been possible without you. Special thanks to all of those who have generously offered mentorship to me over the years, such as Jiajun, Ed, Toki, Rika, Krishna, Manfred, and Ron. And of course, to my previous advisors and colleagues at the University of Toronto, Florian and Professor Hani Najib. I also want to thank all of our industry collaborators, especially Masha and Haruki at TRI, as well as Isa and Saptarshi from NASA JPL. It has been a pleasure to work with all of you. Thank you to all my lab mates at the IPRL and ASL. I was very lucky to have 2 homes during my PhD. And I think you're all extremely talented, will go on to do great things in the field. Please stay in touch in the future. To my friends and to my very close friends from many phases of life, those I grew up with, those from my undergraduate experience and those from grad school, your presence has been completely integral to this PhD journey. To extended and immediate family, I very much cherish your presence and your support, and I'm indebted to you guys. Thank you for all your support. To my parents, Ramon, Sandra, and my sister, Emily, you have served as an inspiration for how I approach every day. I'm very lucky to have you guys, and I look forward to continuing this journey together. Last but certainly not least, to my partner, Steph, this PhD journey has been made very special because of you. Thank you for everything you do. All right. Thank you, guys.
How will opening for you guys? Or I don't know if anyone's online. And for the months, that's that.
Yes.
Talk. I had a question regarding the LLM safety in your work about how you have created a set of potential failure modes. One of the failure modes I noticed you didn't really talk about was this idea of understanding context or subtext from a prompt. For example, when you say put everything on the table, how does it know it's all the things that are on the floor and not some unintended object, say itself or the table, and trying to put it table on the table?
Okay. So, yeah, so the question is, how can we get LLMs to properly interpret the context of their environment? And this relates to actually the comment I was sharing with Eero, which is that what we do is underneath the hood, we abstract the environment into a symbolic representation. So, a set of predicates that define the relationship between objects and where they are situated in the environment that we pass the LLM. And we find that doing so providing a structured representation allows them to reason in a way that respects what's actually in the environment rather than simply just listing all perceived objects. So there is some structure in how we represent the environment to LLMs. All right. Oh, Guillaume?
Yeah. You would remove random shirt from the background. Ways you book that you don't have to say this card that you have your demonstration, but rather just know what's affecting it and still use support of that.
Yeah, absolutely. So I think there are, okay, so the question is, can we go beyond curating out complete demonstrations, essentially be a little bit more efficient in how we curate? And there are 2 different ways, I think, of approaching this. The first is to apply very similar influence function-based techniques, except rather than scoring entire trajectories, we try to figure out what subsegments of demonstrations are potentially responsible for failures. The other approach is to look, I think, not towards necessarily data-centric interpretability tools, but towards model explainability tools that can tell us specifically what concepts in an open vocabulary fashion, it is the white background that's affecting the policy performance. And then us as designers figuring out ways in which we can curate the data to alleviate the effects of these spurious correlations. Yeah. Awesome. Any questions online? No.
us. Wow.
Luis? Yeah.
Basically talked. With the data part, I was curious if you had thoughts on how similar tools, or if similar tools could work to also inform, like, oh, what data would I need to collect? And, like if I wanted to add more data to my data set, right? Or if maybe that would be what we have instead.
Yeah, I think closing the loop with this kind of tool is a little bit difficult because it's mainly it mainly helps you get an understanding of how existing data shaped policy behavior. But again, going more towards model explainability, I think is the way to point toward how you should subsequently inform data collection efforts based on concepts that we interpret. Yeah. Great. Thank you for the questions.
So the